All right, good morning. Happy Thursday. We're moving forward here, almost done with the second week of the quarter already. We are starting up, try this again. We're going to work on some stuff involving our lab and our practice problems today. So, my hope is that by the end of class, you should be really, really close to being done so you can wrap it up and you can take the quiz and have a general understanding of what we're talking about. I have to tell you, I made a bad choice this morning. A couple days ago I was making pizza, like when you get the crust and then make your own. And so somehow I got a whole bunch of cheese on the in the oven all burned. And so I thought this morning, I was like, yeah, I gotta clean that. So I ran the clean cycle. So I've basically smoked myself out of the house. I mean, I'm here, but there's like it's clearing now because I have some windows open, which is so it's like smoky and cold. It's just just not a good start to the day. So I hope your day is starting better. Um, like I said, the plan for today is to be able to talk about the practice problems and be able to get you set up on some of those and make sure you're moving in the right direction, as well as talking about doing some stuff with the lab. And so the hope is that you can be really close to being done, if not completely done, by the time we wrap up today, and that you're in good shape to take the quiz, that you have a good understanding of what we're talking about, and that things are moving forward for you. When we're talking about static electricity, we're talking about this buildup of charges that's causing an interaction between the two objects. And so what happens is, you have your protons and your electrons. Protons are positive, electrons are negative. And if you have more protons on an item, then it has a positive charge. If you have more electrons on there, it has a negative charge. And found in nature, those two charges will either repel or attract, depending on the combination that you have. And so my youngest one has really, really, really fine hair. So I took and I'm gonna share my screen with you. His hair was all staticky on a blanket the other morning. So I have a couple of quick illustrations of what happens with this. You should be seeing my screen right now. There's just the picture of it where the videos go. Um, so just a blanket on his head. You've got you can see that like his hair is standing up as he's moving around. With that, the dog's not amused in the background. Um, but as the blanket is over his head, it's building up that static electricity in his hair, and it's causing his hair to all stand on end and kind of push apart from each other. But then also is attracted to the blanket in the process. So it's just a mess. So that's what we're talking about. It's that force that becomes naturally occurring because of the interaction that you have with those charges. And you've probably experienced this sometimes with a shirt or like pants getting kind of like sucked up against your leg. Skirt or a dress, blankets, stuff like that have the capability to move that pretty easily. So the first thing I want to start with is our lab. And with our lab, if we go to our assignments folder for this week, we have our electric field simulation, the quiz that'll be up this afternoon, and then your practice problems. And so for the electric field simulation, it looks like, nope, I closed that. It looks like this. Come on, go ahead and open it up. The simulation itself, the paper to work on looks like this, and then the simulations are also linked there so you can easily access those. And when you pull them up, the first one is asking that you are just figuring out, it has you put on some charges and then draw what you would experience there. And so the first one on your paper says that you should have two positive charges, or they should be positive, and they are 6 boxes apart. And so on your paper, it looks like this. It says, go to simbucket.com, charges and fields. That's what that link takes you to. Set up the arrangements listed below. Trace the field lines onto each screenshot. So positive, 6 boxes apart. We have that set up. And what you're not going to draw these tiny little arrows. What you're looking at is actually what the field lines would look like in this situation. And so you will have on your drawing, then you can see that these, with the positives, if you want to make your lines darker, just add a charge on each one, and it'll make them a little darker for you to see. You want to make them darker than that, add another charge, just to kind of see what you're talking about a little bit more. And with these, you can see that it comes this way and then it goes up, comes this way and then it goes up in the middle or down in the middle. And we have that, these little arrows should help us direct how we draw the field lines, but they're not necessarily, you don't need these lines as is. And so for this, I'm actually, wrong thing. I'm actually going to take a screenshot of it like this. I'm going to screenshot this thing now that I have them on there. And then if you want to do that, you're welcome to. And then I'm going to just draw what these lines would look like on there. And so from here, I can take, can I do that? Nope. I can add a shape. And the thing that's nice about these arrows is they are, switch this to black. They are, they have that little part in the middle that you can move them. So I can put this here. I know it's going to be going up here, and I can move this like this so it actually follows kind of the pattern that you have. And so if you want to do this on a draw program on your iPad or on your computer, you can. If you just want to do it like drawing the lines with your finger or a stylus, you're welcome to do that. Whatever works best for you. You know, on your iPad, you can probably draw them pretty easy. So whatever that looks like, but we're looking at actually the field lines. I'm going to just switch colors on this so you can see them. I'll make them pink. So if I add another line, whoops, I want an arrow. If I add another arrow here, it can look like this. Put that here. I can put this down here. And so remember that with our field lines, they're always going to push away from the positive and down toward the negative. And so you can kind of get that to the place that you want. They're not going to cross. And you're going to get that kind of figured in the way that it normally would go. And so you're taking and you're adding those on there. I'm doing it on a screenshot. If you want to do that, you can. It'll help you follow the lines a little bit better. Or you can just do it on the paper. You know how those lines should look based on the line rules that we have. And so instead of doing it on a screenshot, you can just put your put a charge here and draw it on there. So you can just add a little circle, or again, with your iPad or on another piece of paper, you can just draw it freehand. There's nothing wrong with that. So depending on what you have, you'll get those drawn on there, 6 boxes apart. Move this over here, 6 boxes apart, and then you can draw those field lines on there. When it comes down to this one here, it asks for a positive and a negative 8 boxes apart. So I'm going to move this here and go 8 boxes apart. Approximately, it's not the end of the world if it's not exact. Change this to red because it's a negative charge, and then you can see what's going on with that. We can go back to our simulation. When we do that, I'm going to to get rid of one. Well, I'm just going to clear the screen. I'm going to go positive. I'll do a negative, 8 boxes apart. It'll be about right there. Again, if you want to make it darker, just add some on top. It'll strengthen the magnetic or the electric field around it. And so you'll be able to have the ability to see that. And so you have those. You can see those really clearly here. Again, I'm just going to screenshot this because then I can follow the lines. So I've got this screenshot here. And on this one, you have the positive and the negative. And so the blue is going to push away the charge and the red is going to draw it in. So if I put in an arrow here, I'm going to just keep them in pink so you can see them easily. I can just follow that one straight across. I'm going to take and do this one. I'll put it here. It's going to start here. It's going to end here. And then I can take that middle bar and just pull it down here so it's in line. I can do that again with the top one. And I'm not fully completing each of these. That's going to take a while. But you can kind of get a feel for what's happening here. And so you'll go ahead and you'll get your lines on there. Again, you're drawing what the electric field lines should look like. And so they'll be the actual lines, not just the teeny tiny ones. And you'll be able to get those from there. And so you're filling that around. You're filling that around on each of them. The thing that'll happen then on the other two, so you have 4 of them on your page. On the other 2, it asks that you pick, it says to arrange any 3 or 4 charges and draw the results below. So you decide where you're going to put those. Ways that you can do this well, I'm going to clear this. You can go, if you want, you can do a positive in the middle and a negative over here and a negative over here. That's one that can be one that's not too crazy to have to draw. You could do 2 positives, positive here, and then a negative over here. You can put something up here. However you want to do that is up to you. But pick two different configurations that you want to do for that. And then you'll put those in these 2 spots. And again, you'll put those on and then you'll draw the field lines of what is being created on there. Again, the field lines are visually representing what that electric field would do if you dropped a test charge in there. And the test charge is a teeny tiny positive charge. Any questions on this part of the simulation that you need to do? The next part can either be really fun or really frustrating. My hope is that you have some fun with it. If you get to the frustrating point, just draw what you have, show the path of where the puck goes on here, and then just say it didn't work. But I want you to try them, and I'm going to show you. We'll do the first one together here. And this one is, you're using a different link on this. It's still on the page. It's the one that is... that looks like this. I'm going to go ahead and clear this completely and go back to level 1. And so if you have it, go ahead and pull it up. Level 1, you're just trying to get the puck into the net. There are no distractors along the way. You have a couple of different ways you can do this. You can take the negative and say, well, positive attracts to negative, so you can put that back there. Maybe. Wahoo! Got it to work. Or you can clear the screen and put a positive here. Positive sometimes, if it's a little bit up or a little bit down, can sort of give you a weird outcome, but let's see if I can get it the first time. Okay. There we go. Yeah, I got that. So depending on how you do that, you can just draw what you have. On here, when it comes to drawing, if it's helpful for you to draw all the field lines, do it. If it's not, don't. And so what that can look like for this first one, I can just say, let's take my red charge here. Go ahead and paste it and bring it down. Okay. Not like that. There we go. Bring it down. I can just say, I love when things, whatever, we're going to go like this. Try it again. Can I do that here? Nope, I have to do a new circle. I'm going to go ahead and put it right here. Very large charge. I'll put it here. It's behind there. I put a positive charge behind there, and then I took and it went straight in. So you can just draw something like this and show what's happening with where it went. It's not aligning nicely. There we go. So that went in. And so you can just do something like that. On the other ones, they end up getting a little bit trickier. So you're going to pick the level and show what you did. And so if you have it up, I just want you to take a moment and work on it. I'm going to try it as well. I was not successful last hour. I'm going to try level 2. So take a moment and try it. We're going to take 2 minutes to see if anyone can get it. If you get it, pop on and let me know I got it and tell me the level. If you get it, or if you want to just type it in the chat that you got it, you can do that. As for right now, we're just going to give this a try. So mine's not working. That's cool. Better. Not better. Better. Not better. So it's not super easy, but it should work eventually. Oh, should be in the keyword there. Okay. So sometimes they'll like go shooting off here and then they'll come back, and that's always amusing to me. Let's see if I can make that happen. Nope. Anyway, so you can keep trying these. If you get a good one, just shoot me a screenshot on email and let me know that you did it. So here's the deal. As you can see, this can get frustrating really quickly. So if you get, the biggest goal here is that you are looking, you're seeing how the charges interact. And you're seeing how by creating that electric field, the puck will travel in different ways depending on what charges you have in each spot. And so the goal is that you take some time experimenting with it, seeing what you can get. If you happen to get a goal, that's awesome. If you don't, still write the level, draw what you did, and just write that it didn't work. Write the level, draw what you did, and write that it didn't work. If you do it and draw what you did and say it worked, I will celebrate with you because that's fun. So that's what you're looking at on your simulation stuff. This one, you're just setting up and looking at how the electric field looks. And this one, you're looking at how a test charge interacts within that field. Any questions on either of those? Okay. Next thing is I want to talk about the practice problems that we're doing. So if you don't have your practice problems out yet, or you don't have something to write on, go ahead and get that, please. And we're just going to talk through the problems. Number one, we'll talk about briefly. Number two, we'll take some time on because it's a similar kind of setup to what we've been doing and the different things that go along with that. And then 3 is goofy. It's not hard. It's just a little goofy. And then 4, 5, 6, and 7 all involve the equation that we're working with, and we'll get you set up on those. And then I'll talk about what to do on number 8, and that will probably bring us up to the end of class. So number 1, how do we classify the 2 types of charge? So the 2 types of charge that we have are positive and negative. They are naturally occurring. So protons are naturally positive, electrons are naturally negative. If an object has more protons than electrons, it has an overall positive charge. If it has more electrons than protons, it has an overall negative charge. The protons are locked in the nucleus. The electrons, some of them are free to move around. And so that's how those charge differences occur. How do the forces vary with plus, 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 minus, and negative, negative? Remember, opposites attract. So positive, negative will pull together. You have a positive on one side and negative on the other. There's a force that is drawing them together. If you have positive, positive, they'll repel. If you have negative, negative, they'll also repel. Let's talk about these situations in number 2 here. It says, consider a pair of electrically charged coins hanging a certain distance from each other. And so a lot of times with this, we talk about something that's hanging so there aren't other forces that are in there. And so you have Q1, I'll show you my board in just a minute, Q2, and a distance in between them. And so for A, it says if the charge of one coin were to double, how would the force compare? And so looking at this, I'm going to go back to here, pin this. Looking at this, we know that the equation that we have is Fe equals K, Q1, Q2 over D squared. Cool. So what? What if we double something? Well, so if I say Q1 is times 2, I'm going to rewrite this equation, F of E equals K. I'm going to say 2Q1 because it's double what I had before, Q2 over D squared. Well, remember when we're doing something like this and we're looking at if we change one thing, how does something else change? Whatever happens here also happens to the force. So I'm going to pull out the 2 so I can isolate that. I know what happens. And whatever happens here also happens to the force. So the only thing that happened here was that I had a 2 and it's on top, so I don't have to worry about anything else. The 2 is out. It is what is happening to the force. So I know if I double one charge, then the force is also times 2. So if you want to screenshot that, go ahead. I'm going to erase some of it in just a moment. And we'll look at B. This should look a little bit familiar because it's stuff that we have done before, just using different equations. Looking at B here, B asks if you double both charges. If both charges double, what happens to the force? So we know that this one pulls out and gives us 2. Then if we also double this one, so Q1 is doubled and Q2 is doubled. So this 2 also comes out. So this, both 2's here, this 2 comes out, this 2 comes out, 2 times 2. These numbers are multiplied, so we'll multiply these. 2 times 2 gives us 4. So if Q1 is times 2 and Q2 is times 2, if both of those happen, then both 2's pull out and are multiplied, and that leaves us with a force that is times 4. So you have, if you double the charge, you double the force. If you double both charges, the first one doubles the force, and the second one doubles that. So 2 times 2 gives us our 4. Again, whatever's happening here can come out, and that's what's happening to the force. I'm going to erase that, so if you want to screenshot that or finish writing it down, go ahead and do that. And I'll take this off. The next one, for C, it says, what happens if you triple the distance? And try this again. There we go. If you triple the distance. And so we say D is times 3. This anything that shows up on the bottom is a little bit goofy. So let's look at it. We have our electric force, K, Q's stay the same, Q1, Q2. And now we're going to triple the distance. So I'm going to say 3D, and I'm going to square that whole thing. Well, when you square that whole thing, you both square the 3 and the D. So I'm going to rewrite this. So V equals K, Q1, Q2 over, I'm going to square the 3. So 3 squared is 9. I'm going to square the D, D squared. So what we have, the thing that has happened is that we have a 9 that's here that wasn't, and it's on the bottom. So when we pull it out, we can't just say that it's 9 because it's on the bottom. It's on the bottom of what? It doesn't show anything. If it doesn't show anything, it's just a 1. So whatever happens here, whatever we can pull out, it also happens to the force. So if our distance triples, our force is times 1/9. So it's a lot smaller just by tripling the force there. Any questions on that one? Also screenshot it, please. All right, and the last one's probably my favorite. I know I shouldn't have a favorite, but I do. And this one, we start again with FE equals K, Q1, Q2 over D squared. And in this one, it says both charges double and the distance doubles. So Q1 is times 2. Q2 is times 2. D is times 2. So everything that we have here will double. K is a constant. It's not going to double, but the rest of our variables will. So we have f of e equals K. We'll say 2Q1, 2Q2, 2D, and we'll square that whole thing. So let's pull some numbers out and see what's going on here. I pull out the 2 here, pull out the 2 there, I multiply those to get 4 up top. So I can say f of e equals K. I can say 4 Q1, Q2 over 2D squared. Let's do this at the same time. The 2 is squared, so 4, and the D is squared, D squared. Well, if you look at this, what happens to the 4? Well, 4 on top, 4 on bottom means that it divides out and cancels out. And we're just left with K, Q1, Q2 over D squared. So the force stays the same. It stays the same. Numerically, this happens because you have two 2's up here that multiply to be 4, and a 2 squared down here that also multiplies to be 4, and the 4's cancel out. Conceptually, this happens because when you have larger charges, they have more strength. And when they have more strength, they can reach farther. And so even though you're separating them by a larger distance, their strength allows that force to also increase. So as the force, the relationship of the charges increase, the distance also decreases, and then it cancels out because it all happens to be 2's. So go ahead and screenshot that. Any questions on that one? The next one I want to talk about is number 3. And number 3 isn't super hard. It's just sort of goofy figuring out what it looks like. So it says that one...
Get that. Could you try again?
I'm sorry. Apparently Siri thinks I'm talking to her. An electron has a charge of 1.60 times 10 to the negative 19th coulombs. So the negative is irrelevant in this, but it's there. So that's the charge on a single coulomb. So if I have on a single electron, and if I have 1 coulomb of charge, and I can assume negative if I want because it's made up of electrons. If I have 1 coulomb of charge, how many electrons does it take to make this up? So here's my coulomb of charge. How many electrons do I need to get in here in order to make up that full coulomb? So I'm going to take the whole. I'll take my 1 coulomb divided by the teeny, 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 tiny parts. 1.60 times 10 to the negative 19th. I can put negatives on there. They cancel out. And when I take that, I'm breaking up this single coulomb and all of my electrons on the inside so I take the whole divided by the number of parts the amount in each part. And that's where I get the 6.25 times 10 to the 18th electrons. And then that's it. That's what we're looking at. So it's not an equation problem. It's more of a thinking problem. And saying, all right, if I have this whole bit here, how many of these teeny tiny pieces need to go in there? It's like saying this is the mass of one, or the volume of 1 drop of water. And this is a full swimming pool full of water. How many drops do I need? Well, swimming pool divided by the drops would tell me how many drops that I need. And so that's what we're looking at here. Any questions on that one? This is number 3. Guys, go ahead and screenshot it. All right, I'm going to erase that. 4, 5, 6, and 7 are all dealing with the equation of f of e equals k q1 q2 over d squared. And so in number 4, it says that both of the charges are the same. And so you'll pull your variables q1, q2, d, f of e, and k. And we know that k is always 9 times 10 to the 9th. And in 4 and 5, we'll be looking for the force. And so this will be what we'll be looking for each time. In number 4, it says 2 pellets each with a charge of 4.5 times 10 to the negative 6 coulombs. So both of them have that. And the distance between the two is 0.25 meters. And so on number 4 here, we're just looking at how do these numbers go into the equation so they appropriately work. So we have our k value that will go there. Q1 goes there. Q2 goes there. That ends up being arbitrary because the 1 and the 2 just let us know that we have 2 charges at the top. And then the 0.25 meters will go on the bottom, and it will be squared. And so getting that one set up is going to look something like that. Go ahead and screenshot that if you would like. I'm going to move on to number 5. Number 5 is very, very similar. We just have a different charge up here We have a different charge here. I think it's still 10 to the negative 6, and we have a different distance. And so in number 5 here, we end up with two metal spheres are separated by 0.6 meters, 0.60 meters. One has a charge of 5.0 times 10 to the negative 6 coulombs. The other has a charge of 8. It says 8 point, should be 8.0 times 10 to the negative 6 coulombs. Calculate it. So again, same placement on these. We're just sticking different numbers in. So numbers 4 and 5 are intentional on making sure that you are figuring out where to put the charges appropriately first, or the variables. Any questions on number 5, or let's go ahead and screenshot that. Six and 7 both involve rearrangements. And so I'm going to go ahead, let's erase all of that. Number 6 asks, two foam balls each have a charge of 9.1 times 10 to the negative 6 coulombs. So Q1 equals 9.1 times 10 to the negative 6 coulombs. Q2 also equals 9.1 times 10 to the negative 6 coulombs. And it says that they're being pushed apart by a force of 2.0 newtons. And we want to know the distance. And so this one sets up like this. We're going to need to solve for distance. So we start with f of e equals k q1 q2 over d squared. To find the distance, we need to multiply both sides by d squared, sorry. And it cancels out here. And we can't have d squared combined with the force. So we also need to divide by f of e. So at that point, that gives us that d squared is equal to k q1 q2 over f of e. We also can't leave it squared. So we're going to take the square root of both sides. And in doing that, I'm going to move this over here because then we'll just kind of keep rolling here. We'll have d is equal to the square root of k q1 q2 over f of e. That's goofy. There's a lot of stuff going on here, but let's go ahead and put our numbers in there. Remember that as long as you're getting all of your steps shown appropriately and they're correct, then a calculation error is not going to hurt you. So let's look at this. We've got k. We know k is 9 times 10 to the 9th. We have q1, so 9.1 times 10 to the negative 6th. 9.1 times 10 to the negative 6th for our other charge, divided by 2.0 newtons for our force. A lot of stuff going on there. So we'll calculate it. We'll say 9. Remember to use your EXP button or your E button to keep your numbers together. We'll take 9 times 10 to the 9th times 9.1 times 10 to the negative 6th times 9.1 times 10 to the negative 6th. Then I'm going to divide that by 2. And so I get, with this, I end up getting that d is equal to the square root of 0.372645. I need to take the square root of that number. And so d is equal to 0.61 meters. So that's the whole one on this one. You want to take a screenshot. Sorry, I didn't get it all on there. Screenshot at the top if you'd like. And I'll slide it up in a moment and you can take the screenshot on the bottom. Screenshot on the bottom. I try to get it aligned so it's a single screenshot, so I'm sorry when that doesn't happen. Any questions on that one? Again, there is a video that has the rearrangements on it. There's also, the rearrangements are also given in the printed overview that you have. So whichever works best for you figuring it out, it's available to you in whatever you need. Number 7, let's look at number 7. Number 7, in this one we're going to solve for one of the charges. And so it gives you that a small sphere is placed 0.5 meters from 9.5 times 10 to the negative 6th coulomb charge. So our distance is 0.50 meters. Q1 we can say is 9.5 times 10 to the negative 6 coulombs. Q2 is what we'll be looking for. It tells us that our force is 1.5 newtons, and we know that K, 9 times 10 to the 9th. And so in this one, we'll be solving for Q2. It doesn't matter which Q you're solving for, you rearrange it the same either way. And so again, we're going to start with f of e equals K, Q1, Q2 over d squared. In order to solve for Q2, the first thing we have to do is to multiply both sides by d squared. And so we're at this point, we have d squared times f of e equals K, Q1, Q2. We need to keep Q2 on its own, so we'll divide both sides by K, Q1, K, Q1. These cancel out over here, and you're left with this equation that Q2 is equal to d squared times your force divided by K and Q1. Remember, when you are multiplying these on the bottom, you need to put parentheses around that multiplication in your calculator. I'll let you finish up that one later. This is number 7. If you want to screenshot that, go ahead and do that. And then I'm going to talk about number 8, and we will be wrapping up. We only have a few minutes left. Again, my hope is, I know these are kind of goofy problems. My hope is that by being able to work through it and talk about it and get some started, that then later today you can wrap these up and take your quiz and be in good shape. The quiz will be up this afternoon, and then you can do it sometime before the end of the day tomorrow. I'm going to shift over here and look at number 8. So number 8 has 3 different electric field drawings, and you're using what you know about these to figure out what's happening. So it says use the electric field diagram to determine the correct answer. So the charge on the left is positive or negative. The charge on the right is positive or negative. And the charge on the right is equal to 2 times, 3 times, 4 times the charge on the left. So what we're looking at here, the charge on the left is positive or negative. So we need to look at the arrows. On both of these, the arrows are going into the charge. Well, if the arrows are going into the charge, what does that tell us? Well, we know that the arrows for electric fields are always pointing toward the negative. So on this one, arrows are pointing toward this one, so it's negative. On this one, pointing toward this one, so it's negative. So I'm going to take and circle. Charge on the left is negative. Charge on the right is also negative. Then it says the charge on the right is, it gives us some options, the charge on the left. Remember that comparing the two charges happens by looking at the line densities. And because on this one, we can see that there's equal line densities. You have the same number of arrows over here that you do over here. That tells us, it doesn't tell us what the charge is, but it does tell us that those two charges are equal because they have the same amount of lines around them. So we can put equal to there. And you'll continue with that. Charge on the left is, charge on the right is, using the direction of the arrows to determine it, and then how they relate. And again, left, right, and then how they relate. Any questions on number 8? All right. Then we are getting to the end here. I know that's a lot of stuff. Hopefully it's helpful in helping you move forward. Things to keep in mind, these are your first assignments of quarter 3. So please, please, please do your best to get those in. Do your quiz, do well on your quiz, start quarter 3 strong. Quarter 3 has a tendency to move by quickly because we don't have a lot of breaks in there. And we're already getting to the end of week 2 because we started a few days late. So we are moving forward. We are moving, forward quickly, and we'll keep figuring things out as we do that. So get your work in, work on your quiz, keep doing what you're doing. Thank you for being here. It is huge that you're showing up, and that's always, always helpful. Not only because you can hear a little bit about what's happening, but hopefully you're getting some just some guidance in what you're doing, and so you can be figuring it out and being successful with that. So I'll hang on if you have any other questions. Other than that, have an awesome day, and I will see you all next week. Bye-bye.